about introduction of titration. So, I will explain to you the definition of titration. The process of titrating involves slowly adding one solution with a known concentration, referred to as a titrate, to a known volume of another solution with an unknown concentration until the reaction approaches neutralization, which is frequently signaled by a color change. For something to be a primary or secondary standard, a substance known as titrant has to meet the prerequisite size. Titrant, in its broadest sense, is a method for figuring out how much of an unknown solution there is in a given sample. The process of titration is used to figure out the solution concentration. The simplest sort of titration combines a strong acid and a strong base that totally dissociate in water, resulting in a strong base neutralization reaction. This is the case with titration of a strong acid and a strong base. Next, we will talk about methodology. What is methodology? The word titration methodology refers to a laboratory procedure for figuring out how much of a material is in a solution until a chemical reaction between the two is complete. A solution with a known concentration, referred to as the titrant, is gradually added to a solution containing the material being examined, referred to as analyte. The titration method is based on stoichiometric principle, which connects the quantity of reactants and products in a chemical reaction. The concentration of the analyte can be determined by precisely measuring the volume of titrant needed to meet the reaction endpoint. There are many methods to do titration and many steps of it, but we will go with a general step. First of all is preparation, then titration, endpoint detection, and the last one is calculation. So we have known the general step, right? So we will go on with the method step. So I will explain further about the method that we use. First is preparation. Preparation is the analyte solution is prepared, and any necessary indicators or pH buffers are added to facilitate the detection of the endpoint. Second, titration. The titrant is added gradually to the analyte solution, typically using a burette. The mixture is continuously stirred or swirled to ensure proper mixing. Third, endpoint detection. The endpoint is the point at which the chemical reaction between the analyte and titrant is complete. It is often indicated by a color change using an indicator or a change in pH. Visual cue or instrumentation, such as a pH meter, can be used to detect this change. The last one is calculation. The volume of titrant used is recorded, and calculations are performed to determine the concentration of the analyte in the original solution based on the stoichiometry of the reaction.
Next, the examples of titration applications in food industry. The main application for our presentation is determination of vitamin C content in food and beverages. So, how can we determine the vitamin C content in food and beverages by using titration? We can use iodometric titration. What is iodometric titration? Iodometric titration is an analytical technique frequently used to ascertain the quantity of oxidizing or reducing agent in a solution. Or we can call it as a redox titration, where the appearance or disappearance of elementary iodine indicates as the endpoint. So, how does the ascorbic acid or vitamin C works with iodine? So, vitamin C present in foods and beverages is a reducing agent. Iodine can oxidize it when the environment is acidic. This is how ascorbic acid and iodine react. So we have ascorbic acid plus with iodine, and we will get benzene hexol or dihydroascorbic acid plus 2 iodine and 2 hydrogen. As you can see in the first picture, ascorbic acid will turn to dihydroascorbic acid by oxidation reaction. But rather than oxidation reaction, we can also combine the iodide and iodine to form the triiodide. And this triiodide will oxidize the vitamin C and turn it to dihydroascorbic acid. And as long as this vitamin C present in the food sample or solution, the triiodide will be converted and change quickly to the iodine ion. And moreover, if the vitamin C has been oxidized fully, the iodine and triiodide will combine with starch and will change the solution color to blue-black. As we can see in the picture, the starch indicated turns to purple or black. But if we do the experiment, it is commonly to be blue-black. So The blue-black color will be the endpoint of the titration.
Next, we need to prepare the solutions. First, we need to prepare 1% starch to indicate the solutions. First, we need to 5 distilled water that is almost at a boil. Then we need to add about 0.5 gram of soluble starch. Then we need to mix it thoroughly and let it cool before we use it. Next, we need to prepare the iodine solutions. First, 200 ml of distilled water are used to dissolve 5 gram of potassium iodide and 0.268 gram of potassium iodate. And then 30 ml of sulfuric acid 3 molar is added into the solutions. And this solution will be poured into 500 ml graduated cylinder and it will be diluted with distilled water until it has a final volume of 500 ml. And then we need to mix the solutions. After that, the solutions will be transferred into 600 ml beaker. The iodine solution should be marked on the beaker. Next, we need to prepare vitamin C standard solutions. First, we need about 0.25 gram of vitamin C, or known as ascorbic acid, to dissolve it into 100 ml of distilled water. Then, we need to fill a volumetric flask with distilled water and dilute it to 250 ml. And the flask should be labeled as vitamin C standard solution. To standardizing the solutions, we need 125 ml of Erlenmeyer flask and add about 25 ml of standard vitamin C solutions. And then we need to add about 10 drops of 1% starch solutions that we have been prepared earlier. And third, we need to fill the burette after rising it with a small volume of iodine solutions, and we need to record the volume. After that, we need to titrate the solution up until the end point is reached. After swirling the solutions for 20 seconds, the indications of a persistent blue color will appear, and the final volume of iodine solutions will be recorded. The initial volume minus the final volume will give the result of volumes that is required. And lastly, the titration will repeat at least twice more, and the result should be obtained within 0.1 ml. We need to determine the concentrations of vitamin C. First, we need to use a balanced chemical reactions between the iodine and the vitamin C. The chemical reaction usually from ascorbic acids adding with the iodine to produce dihydroascorbic acids and 2HI. And then, for example, if the reaction requires 1 mole of iodine and 1 mole of vitamin C, so the molar reaction would be like 1/1. And then we need to convert the volume of titrant solutions. After that, we can determine the moles of vitamin C. How to determine the moles of vitamin C? We can determine it by using the molar ratio that we have obtained earlier. And lastly, we can calculate the concentrations of vitamin C.
So, for the example experiment, we choose determining the vitamin C content in fruit juices, and this is the complete describe for apparatus and type of solution.
Now, I will give the example experiment related to this topic. The experiment is iodometry determination of the ascorbic acid vitamin C content of some fruit consumed in a university community in Nigeria. The ascorbic acid content of 7 different fruits: grapefruit, lime, orange, tangerine, banana, pawpaw, and pineapple was determined by the iodine titration in order to know which fruit will best supply the ascorbic acid need for the body. The experiment began after removing the peels and slicing them in half transversely. The experiment got underway. The orange, lime, grape, and tangerine fruit juices were extracted, and 2 grams each of the pineapple, pawpaw without seeds, and banana fruits were turned into fine pastes before being diluted with distilled water to make 50 ml. Iodine titration was used to determine the amount of ascorbic acid. The starch solution reacts with iodine to give a purple color. The production of the purple color is prevented by the presence of vitamin C in the solution, which neutralizes the iodine. As a result, the concentration of vitamin C in a solution can be determined by adding a little amount of acidified starch. Reaction makes first, followed by iodine drop by drop until the solution turns purple. The appearance of the blue starch iodine color is the endpoint. Iodine reagent was standardized by titrating it against 5 ml of 1.00% ascorbic acid. 3 drops of 1% starch were added until the appearance of the blue starch iodine color appeared. 5 ml of samples were then treated the same way. The iodine solution was prepared by dissolving 5.00 gram potassium iodate and 0.368 gram potassium iodate in 200 ml of distilled water, and then adding 30 ml of 3 molarity sulfuric acid before making up the volume to 500 ml with distilled water. Results show that tangerine had the highest value of ascorbic acid, followed by pawpaw, orangey, grape, lime, and banana with pineapple having the least value. It therefore follows that tangerine would supply more ascorbic acid per serving for body need to compare to the other 6 fruit. As the iodine is added during the titration, the ascorbic acid is oxidized to the hydroascorbic acid while the iodine is reduced to iodide ions. Due to this reaction, the iodine form is immediately reduced to iodide as long as there is any ascorbic acid present. In conclusion, our result shows that tangerine would supply more ascorbic acid per serving for body need to compare to the other 6 fruits with its daily value percent being more than twice that of the lime and more than 7 times of pineapple. Now, we have concluded this topic. With the add of indicator, the endpoint of the titration is found when the color of solution changes as a result of neutralization. It is possible to link the concentration of the AC to the concentration of the base by calculating the volume of titrant needed to achieve the endpoint. To sum up, titration plays a key part in our daily life by offering a reliable and precise technique for a range of applications. Titration can be used in a variety of industries, including the food sector, medical field, and pharmaceutical industry, as we had previously stated.